Hello, everyone. Welcome to my channel. In this part of nucleophilic substitution and elimination reactions, we are going to talk about how to predict products. If you are struggling a lot with predicting reaction mechanisms given reagents and reactants, this video is for you. So let's get started. This is part 5 for nucleophilic substitution and elimination reactions. Here we are going to basically compile what we have learned so far. How to predict the products of certain reaction where we have alkyl halide and some kind of reagent which can function as a nucleophile or a base, and what kind of mechanisms that we have to choose, and after we choose the mechanism, how we can predict the product from regiochemistry and stereochemistry perspectives. And then we will talk about what kind of substrates can participate in these substitution and elimination reactions other than alkyl halides. We will see their structures and their properties and if there's any difference from their alkyl halide counterparts. Let's get started. So these are the sections that we are going to cover. We will introduce this the idea of mechanism prediction, and then the first important point, the function of reagent, how to detect that, the certain reagent that we have, what kind of function does it have? Is it nucleophile or is it base? Then the prediction of mechanism according to what we have found so far, and then some reagents that are on the borderline. We cannot say that if it's strong base or weak nucleophile, we cannot fully determine that. So we will discuss what kind of prediction we have to make in the case of those reagents. So let's get started. And sometimes you have clearly one pathway, but sometimes the substitution and elimination compete in the same reaction. For example, in this case, you have only one mechanism because you have a sodium or methyl and this is tertiary. You cannot have any SN2 reaction and your E2 product is your only product. But sometimes you can have multiple mechanisms. As you can see here, you have a secondary alkyl halide, sodium OH as your reagent, and you form both E2 products and SN2 products. Obviously, one is major and then others are minor, but this is the case where multiple mechanisms compete. So we never should assume that only one product forms. Often a mixture forms. Our goal is to be able to predict all possible products from certain reaction and then identify which one is major and which ones are minor. And in order to do that, we follow three-step approach. First, we determine function of reagent. Is it nucleophile? Is it base? Or is it both? Then we analyze the substrate. Is it primary? Is it secondary or tertiary? Once we find these two, we should be able to narrow down the mechanism. We should be able to say that this is SN2 mainly, or maybe mixture of E2 and SN2 where E2 dominates, or maybe none of the mechanisms will work here, or it's just exclusively SN1. Those kind of conclusions we can draw based on these two analyses. And after we find out the mechanism or mechanisms that we can propose for the specific reaction, we consider this regiochemistry and stereochemistry. For example, in the case of E2 reaction, Zaitsev versus Hoffman, or E or Z, or in the case of SN2 reaction, inversion of configuration, which is a stereochemical evidence for SN2 reaction. So we basically compile all of our knowledge and apply to that mechanism that we have chosen. We are going to first start from the function of the reagent, and in this specific substitution and elimination reactions, we can have either reagent acting as a nucleophile. So in the substitution reaction, the reagent acts as a nucleophile, and this nucleophilicity is a kinetic phenomenon. It depends on the rate. So definition of nucleophilicity is the rate at which nucleophile attacks a proper suitable electrophile. That's the definition of nucleophilicity. So it's all about the rate, right? And this nucleophilicity is influenced by polarizability and the presence of high electron density. So we already said that, for example, whenever we have a negative charge, we say that it's quite a strong nucleophile. For example, OH minus versus H2O. H2O has only lone pairs, but OH minus has lone pairs but a negative charge. So we have this high electron density. So that makes OH minus a very strong nucleophile. It also depends on polarizability. So the definition of polarizability is that ability to spread electron density evenly with some external influence. So that's the definition of polarizability, but we usually consider polarizability to be equivalent as a size in terms of trend. So the larger the molecular ion or molecule or atom, the further away it can hold electrons from the center,
so more polarizable it is. For example, sulfur and oxygen. Sulfur polarize electron density much better than oxygen, so it's more polarizable, so it's better nucleophile. Then we also have a base that we will see in elimination reactions. And this is thermodynamic phenomenon because it's all about stability and it's influenced by the conjugate acids pKa, right? So if we try to find out that if certain base is strong or not, we have to check this reaction. Its conjugate base is being deprotonated to give base and hydrogen plus to the solution. So for base B, we use this equation and then we check the pKa of BH plus. If it is lower, then that means Ka is higher, and Ka is higher means that its conjugate base B is stable. So if it is stable, and we know that stability is inversely proportional to reactivity, so if it is stable, then it's less reactive. Less reactive means less basic. So technically, we don't have to memorize it, but if the conjugate acids pKa is lower, that means basicity is also lower through this relationship. So in order for base to be strong, its conjugate base should have higher pKa. The lower pKa, higher Ka, strong acid. So if it's strong, that means it's going to the right. So this is stable. And if it's stable, then it means it's less reactive. That's how you have to think every single time. So that's thermodynamic phenomenon, and we use this ARIO, atom resonance induction and orbital effect, in order to assess the basicity, how stable the base is, how reactive it is. So we can use as an example. So we can use bromine minus as an example. Bromine minus is a strong nucleophile, at the same time weak base. So how do we arrive at this conclusion? Because it's large and polarizable. Bromine is quite large. So it's actually, considering polarizability factor, bromine is a quite strong nucleophile. So it's going to attack really fast to the proper electrophile. That's like nucleophilicity. We try to understand nucleophilicity from kinetic perspective because it's kinetic phenomenon. But on the other hand, bromine is large and electronegative. It's stable. It's weak base. And also hydrogen bromide, its conjugate acid, is quite strong acid. Its pKa is low. Since conjugate acid's pKa is low, bromine minus is actually a weak base. So this is how we are going to analyze the certain reagents, whether they are nucleophile or whether they are base. And based on this, we can actually categorize them into 4 groups, and you can see this table. We can classify these reagents into 4 categories: strong bases that are weak nucleophiles, strong base and strong nucleophile that can act as both, and the category where they are weak bases. Some of them are strong nucleophiles, but some of them are weak nucleophiles. So this is obviously not rigid classification because some reagents fall in between. For example, cyanide ion, we will talk about this. This is what I call as borderline reagent. But this is strong nucleophile but moderate base, so it does not belong to any category. But in general, this kind of classification is useful for predicting reaction outcome very quickly. So we are going to talk about this category 1 in next slide in detail. I will give you some example and also give you a full definition of DBN and DBU. So this category 2 is a strong nucleophile and strong base. So basically OH, and not just oxide and methoxide, but just most of OR minus. We call them alkoxide. So we will talk about in detail, but they usually favor SN2 and E2 like bimolecular mechanisms because they are strong base and strong nucleophile at the same time, right? And category 3 here is you see halides, halide ion, and some sulfur nucleophiles. As you can see, they are really large, so they are highly polarizable. So that makes them strong nucleophile. But then all of their conjugate acids are actually quite strong acid. Their pKa is low. So in terms of basicity, they are weak. So these reagents usually favor substitution, typically SN2. They do not promote elimination because they are weak bases. Same here. Category 4, they are weak bases and weak nucleophile. Again, because they are weak bases, they do not promote elimination, especially E2. They usually favor SN1 and E1, like unimolecular mechanisms. But we will talk about that in detail, and all categories and all. We will have a chart where the categories of reagents and also a substrate structure. We will have this 2-dimensional table. And then the key takeaway here is that our first step should be to determine reagent category This helps to predict substitution versus elimination outcome. And now we're going to talk about specifically this first class, strong base and weak nucleophile. This is DBN, this is bicyclic compound. Obviously we don't have to know the whole name, but it's just D come from diaza, and B is bicyclo, and N is non-N, DBN, and DBU is undecane. U is refers to undecane. So these are strong bases, weak nucleophile, and this class of compounds are called bicyclic amidins. So this carbon that's connected to two nitrogen at the same time, so sp2 hybridized carbon atom that's connected to two nitrogen at the same time, as a functional group is called amidin, and it's bicyclic because you have fused rings, right? So they rarely function as nucleophile, they almost exclusively function as base, and that promotes elimination. You cannot expect these large crowded bases to attack and replace some alkyl halide, right? They are too large. There would be a lot of steric hindrance. So we do not actually expect them to function as nucleophile. So they almost exclusively act as base, right? So that's why they promote elimination reaction. And the reason why they are very good bases is because after they are protonated, they actually have this positive charge that is delocalized onto both nitrogen. So that's actually quite good stabilization by resonance. So that's why your resulting cations are weakly acidic. Because these are weak acid, that makes this original base as quite strong base. So even though they are neutral, so you don't have any negative charge here, right? No negative charge. So they are neutral. So you expect them to be not very strong base, but because their conjugate acid is weak because of high stabilization, that makes this actually a strong base. Because they would love to get protonated so that they can become more stable. So it doesn't go back because it's very stable. It's happy with its state, this protonated form, because it can delocalize this positive charge onto two nitrogen. And that's a property of amidin. After one of the nitrogen become positively charged, it can actually delocalize. So it makes it very stable. And that's why this original DBN or DBU similarly are very strong. So the reaction outcome with using this DBN and DBU would be E2, actually, exclusively E2. We will talk about that in a chart in the table, but in general, whenever you see this, you have to know that they rarely function as nucleophile, almost exclusively they are acting as base, and you will expect E2 products. So basically we are done in terms of this reagent function. So we have 4 groups, as you could see in previous table, and some of them are borderline. We will talk about them at the end. And we exclusively talk about this first class. So this is how we categorize reagents. And before I move on to predicting mechanisms based on this classification, I would like to mention one case where we show a reagent with, basically it seems like we show 2 reagents at the same time. Because here sodium or ethyl is a strong nucleophile and a strong base at the same time. But this ethanol is a weak nucleophile and weak base. And this is the totally different size of spectrum. So the question is, which one is the reagent here? But the answer here is that this ethanol is actually not considered as the reagent. It's a solvent. It provides a medium for reaction to occur. So it applies to other cases like sodium OH in water. So you will see a lot of cases like sodium OH with water, or sodium methoxide in methanol, or ethoxide in ethanol. So you will see these cases, and in all those cases, this H2O and methyl OH and this ethanol here, they are all solvent. They are not reagents. So whenever you see this kind of a description, make sure that the first one is a reagent, and this is going to be strong nucleophile and strong base, and your judgment is going to be based on this categorization of this sodium ethoxide, because this is the reagent that you are using in your reaction, not this one. This is just the medium, this is solvent. And if you don't show the solvent explicitly, like in this case, you always have to assume that a solvent is present for reaction to occur efficiently. Otherwise, it's almost impossible. Solvent is very important for reactions, not just for substitution and elimination, but in general.
I hope you found this video useful. If you genuinely think that this video cleared question marks on your mind, don't forget to like and subscribe. Stay tuned for part 2, and thank you all for your support.